Okay, double check. It is recording. We got lots of space now. All right. Oh, let's go ahead and check out the exam itself. Okay, I think I worked out most of the solutions already. And some of those are on Moodle as well. So let's go back to Moodle also. Too many tabs. There we go. And the exam is under assembly language programming because that was the last topic introduced. You guys may not be able to see it just yet. Okay, so I'm gonna talk about just the solution. Okay. All right, so this is the for question number 1. The answer to question number 1 is actually not too bad. Okay, some of you went through all the trouble to assemble the whole program, and gave me the actual bytes, as opcode and the entire program. That was not necessary. Okay, that was not intended. I did make it very clear. But I really just need the assembly code like this. Okay, that was all that I needed. So that will pretty much make this one of the shorter questions. The next one is long. Okay, question number 2 is a little bit overboard, but this one is not. So the original code in C in the question itself starts with D equals to 0, and D in that case is register D, and a single instruction can do that. You can either use the mnemonic, which is LDI, D, and then the 0 after that, or you can just say D equals to 0, or you can say D equals to star PC++, and then // a 0, after the comment. So all of those are acceptable as alternatives to this particular format. Okay. Are there any questions about D equals to 0? I think that would be a pretty easy one. And by the way, sub DD works too. Okay, subtracting D from D would also do exactly the same thing. And since we don't really need to look at the flags at this point, so you can mess up all the flags or overwrite the flags, it doesn't bother anyone. The next one is a little bit more involved because the original. This is what is in the question itself. So in the question, I have D plus equal to, and then the expression on the right-hand side is A and 1, okay, single ampersand, not doubles, in parentheses, and then question mark B : 0, okay? And then I wrote out the actual, meaning of the ternary operator, okay? So the first thing you need to do is to evaluate what is A ampersand 1, which is a bitwise AND. So a bitwise AND is done by the AND instruction in the processor. That's your bitwise AND. But you cannot bitwise AND with an immediate constant, so you have to put a 1 into a unused register, which in this case is C. C is the only unused register in this particular program. So you put a 1 into the register C first. Okay, you can also use the alternative way of representing it. And then you perform an AND operation. This is where some people make a mistake of using AND AC instead of CA, because the first operand is the one that gets modified. Okay, so if you say AND AC, then register A is going to be modified, which is not the intention, because the original code is just wants to check. Okay, what is bit 0 of A? Is it a 1 or is it a 0? That was the whole intention. So that's why we want to flip the order and modify register C instead, okay? And because conjunction is commutative, which means the order does not really matter, you can flip the order, it will still give you the same result. The question is, which register are you changing? So change register C, because it's a throwaway register, you can just change it. Now the other thing about the AND operation is it goes through the ALU. Anything that goes through the ALU will change the Z flag. It will affect the Z flag. In other words, after the AND operation, the Z flag will indicate whether register C ends up to be 0 or not. Is that okay? So that's why you can use that immediately, okay? And say, oh, okay, if the result of the AND of the bitwise AND is a 0, then branch around and do nothing, because adding a 0 to D is not doing a single thing. Okay, now some people went through the trouble of actually loading 0 into C and then adding to D. I don't take any points off, okay? It's not wrong, okay? It's just unnecessary. But in this case, but before you do the branch, oh, okay, I made a mistake here. This is JZ, not else, but JCC, because you cannot jump you to a label. You have to use a register to store where you're supposed to go first. So, so just kind of fix this in your mind and say, okay, it's not JZ else, it is JZC, using register C to indicate where to go to. Is that okay? The alternative representation is PC equals 2, and then Z question mark else colon PC. Then once again, this else should be register C. So I made a mistake over there. Okay, any questions? So if you branch around, which is at the end, the else label is all the way at the end of this block here. If you do not branch around, then you want to add register B to D, which is adding this component to this component, which is what you need to do when the condition is true. And then after that, you have the right shift operation. The right shift operation, you still need to use register C to store the 1 because we cannot specify any immediate constants with the right shift operation. And the right shift operation need to change A, so you need to make sure that A is in fact the first operand in this case and not the second one. And then the last operation, I think maybe at least 1/3 to 1/2 of the class got this one, because even though we do not have a left shift operation, adding a register to itself is the same thing as a left shift operation. So that's the whole thing. That's question number 1. Are there any questions about this one? Yep.
When should we get our grades back?
The first one is already graded. I just have not shown the actual grade, but it's already graded. The first one. I don't want to show you guys the. I don't want you to look at your grade only with one question graded. Okay. So this is the rubric. The rubric, I do not put a whole lot of points to D equals to 0 because, well, it's only one single instruction, right? So it's either yes or no. Okay, it's either it's correct or not. And then for the second one, I broke it up into multiple parts. So for the second one, I check whether you know how to do a bitwise AND or not. Whether you know that the Z flag is important in this case, and how to branch around the add instruction, and also how to add B to D. So those are all broken up into multiple points, which is good in a way because it means you can get partial credit even if you don't get one of those things right. And then the right shift operation is its own, okay, because it's one single instruction or 2 instructions to do it. And then the left shift operation is on its own as well. So that's for question number 1. Question number 2 is the one that is a little bit more hairy. Okay, so let me go to question number 2 and look at the rubric for that one. Okay, there we go. Okay, so here's the rubric for the second one. It is in draft mode, which means I have not graded this one yet. The tricky part of this question, again, just reading the first paragraph, is everything that goes through the ALU will change at least the sign flag and the 0 flag. And that has to do with the design of the ALU. Is that okay? So that means you don't want to go through the ALU as you modify register A, or as you try to figure out what bit pattern you have to store in register A. And the question of question number 2, the question itself, in case you don't remember, is I want to copy whatever is in the flags register into register A. That was the intent of this particular question. Okay, is that okay? Does everybody kind of remember what the question was about? Okay. So the trick is, with you don't want to go through the ALU, at least for the 2 flags. Add, subtract, and compare, those are even worse, because in addition to modifying the 0 flag, the Z flag, and the sign flag, the S flag, these 3 instructions will also change the O flag, the carry flag. The O flag is the overflow, the C carry flag, and the L, which is the less than flags. Okay, so those are even worse compared to the other instructions. So to answer this question properly, you need to avoid the use of the ALU instructions while using the J whatever instruction, the conditional branch instructions. There are two ways to do this, okay? There are two ways that I know of to do this, and there might be some kind of hybrid between these two as well. The first one is you can use memory locations to remember the individual bits, okay? And then use a OR operation at the end to OR all the memory locations together. This is the cleaner way to do it, okay? It means you will end up with a shorter code that has more of a regular pattern to it, but it also does use extra memory locations. But since in the question I did not preclude, I did not say do not use extra memory locations, it is allowed, okay? It's not a problem. So in this approach, you will see this particular pattern. Okay, let me just kind of highlight the portion that I intend to highlight. There you go. So this is the repeating pattern. The repeating pattern is basically just setting up a conditional branch, okay, loading a label into a register C in this case, and use a conditional branch to, based on a particular flag, to go to that location. C1 in this case simply means the carry flag is a 1. Okay, and that's why I chose the name C1 to mean that the carry flag is a 1. If I do not branch, then put a 0 into register B, and then store 0 into CF, which is a variable that I reserve later on. Okay, is that okay? So this is the part where it is common. Okay, whether you want to set it to a 1 or a 0, set C as a label is the destination point of storing whatever register B has into CF. Yep.
Can you remind me what the question was?
The question was to store the value of the flags register into register A.
Oh, okay. Awesome.
And there's no direct pathway between those two registers. So you have to go through a lot of code to get the same thing done. Okay. So if I do get to C1 because the JC instruction happens, if I do end up at C1, then I want to put a 1 because the C flag is bit 0. So I put a 1 into register B, then I proceed to kind of fall through the code to store the 1 into CF as a local variable. Well, not local, but into a variable. Is that okay? So this code is repeated several times, like 5 times, because the next flag that I'm dealing with is the Z flag, and you can see it is basically the same code, except the label name is now Z1, and then the conditional branch is using the Z flag for the conditional branch. The other label to set the actual location is called set Z instead of set C, which is down here. And instead of changing CF or the carry flag, I'm changing the 0 flag. And then the value is now 2 instead of 1 because the Z flag is bit 1 of the flag's register. Is that okay? So the same thing is repeated like 5 times, okay, because I have 1 for each flag. So the next one deals with the sign flag. Okay, so this code deals with the sign flag, and the only change is the name of the labels. Instead of using C or Z, I use S in this case for the sign. And also the bit is now bit 2, so that's why I'm using a 4 instead of the 1 and the 2. And then this is the second last one, like here, from here to here. It's the second last one. It deals with the overflow flag instead of the other 3 flags that we have already dealt with. And then the bit number is bit 3, and that's why I put an 8 here instead of the 1, 2, and 4. And then the last one is the L flag, and the code corresponding to that is this chunk here. But you can see that each chunk is almost identical in terms of structure. The only thing that is changed are the names of the label and also the bit, or the constant that I'm setting. This one is a 16 in base 10 because it is bit 4. It's just the bit 5 of the pattern. No, bit 4, sorry. It's bit 4 of the flag's register. So I have to use bit 4 of register A later on. So after changing all those locations, because I have CF, ZF, SF, OF, and LF, okay, Then the rest of this program is looking into those locations. The first one is really just copying whatever byte is at CF into register A because it is the first location. I don't need to zero A in the first place. And then the second one is doing this. Okay, I'm basically ORing register A with whatever is at ZF. And then I OR that with whatever is over at SF, OF, and LF, and that concludes the entire program. Halt instruction at the very end. Are there any questions about this particular approach? Yep.
I have a lot of questions, but this is like a new lesson to me. I couldn't fit it. I didn't know that I could have done this way.
But that's how you write programs. That's how you kind of put things together.
Yeah, but you haven't showed us such a thing.
I did show you all the instructions.
It's the same thing as showing what the numbers are and then don't show how to do the integrals.
I would not say it's the same thing because we know what each instruction does fairly clearly. So it's a matter of how do you combine the instructions to accomplish a particular thing. I mean that's basically what you do with every single type of programming. Yep.
Is LF a memory location?
Yes.
Or?
Those are all memory locations because they're all basically at the end here. And if you want to designate actual locations, that's fine too. But these are all basically reserved locations. They're all initialized to 0. That's what .byte means. But I did not rely on the initialized location. In other words, if they're supposed to be 0, they will be initialized to 0, regardless of how the .byte is specified.
So the LDI instruction saying like right here, it's saying LF, you put that into register C, right?
Okay, so you mean this instruction here?
Yeah.
This is just putting the label LF into register C, which is the address. And then the second instruction is doing the indirect, which means it is actually going to the location pointed to by register C, retrieve that byte, and then put it into register B.
Okay.
Yep.
So why are you using an OR rather than just adding?
You can do add as well, but I'd use OR because these are all individual bits. So OR would do the same thing as add in this very specific case. So you can do an add here because by this time we have already initialized all 8 bytes, so we can use add or 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 any other instruction that goes through the ALU. Is that okay? So you guys ready for the second solution, which in a way is more pure? No, but it's here, so might as well talk about it. Okay, so the pure way to do things is not to use any extra locations. Not that I will take any points off if you do take extra memory locations. Okay, so that's fine. But the other way to do this without using any extra memory locations is more painful, a bit more painful, okay, because it will make the program a little bit longer. But if I see the approach of doing things, okay, even if you don't have enough time to finish it, I will still give you a lot of partial credit, just knowing that you know how to deal with this, okay? So in this case, you basically have to use branching and labels and stuff like that to identify every single one of the 32 possible cases. Now, how do we know there are 32 possible cases? How many flags do we have? C, oops, okay, that is not working. I need a place to put all the pens that are not working. So we got C. Oh, that's not working either. C, Z, S, O, L. Okay, so technically speaking, we have 32 possible combinations because each one of these can be a 0 or 1. Now, some of these combinations should not be possible, after a compare, after an add, and after some of the other instructions. But just to be sure, I want to handle every single one of these. But we know one thing for sure. the L flag is only dependent on the sign and the overflow. So we really technically have 16 cases, not 32 cases. Now 16 cases, we can actually deal with it in a kind of more tangible way. 32 is a bit too much, okay? So now what we need to do is to look at each flag and say, okay, is this flag a 0? If it is a 0, then you go here. If it is not a 0, you go there. The best way to represent this is to use a decision tree. So with the decision tree, this is what we're doing. We first look at a particular flag. It doesn't even matter which one we look at first, okay? I just choose to follow the same order here because this is bit 0, bit 1, bit 2, and bit 3. So I chose to use the same order to evaluate the flags. So I look at C, the carry flag. There are only two possible ways, right? It can either be a 1 or 0. But when the carry flag is a 1, what about the Z flag? Well, technically speaking, the Z flag can also be a 1 or a 0. The Z flag can be a 1 or a 0, right? And then on the third one, I check the sign flag. The sign flag can also be a 1 or 0, a 1 or a 0, a 1 or a 0, a 1 or a 0. And then the last one I check is the overflow flag, which can also be a 1 or 0. So it can be 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0. So once you can figure out this decision tree, okay, each one of these endpoints will basically say, okay, at this time I know exactly what to put into register A. Let's pick one in random. Okay, let's just pick this one. Okay, what is this one representing? The left branch is a 1, the right branch is a 0. Okay, so this is a 1, that's a 0, that's a 0, that's a 1. So in this case, we are saying that the carry flag is a 1, the Z flag is a 0, the sign flag is a 0, the overflow flag is a 1, and because of these two, we also know that the L flag is a 1 because the L flag is always the exclusive OR between the overflow and the sign flag. Is that okay? So you basically, you look at each endpoint and say, at that point, we know what should be in A. So in this case, because C is bit 0, so we know it's a 1, 0, 0, 1, 1 in binary, and this is the constant I should put into register A. So this approach is a little bit more involved because the instruction set that we have chosen can only do a conditional branch based on the flag being a 1, not when it's 0. So we can do conditional branches to go here, and this becomes the fall through case. We can do a conditional branch here, this becomes a fall through case. We can do a conditional branch here, this becomes a fall through case. Is that okay? So the rest of the code is like this, okay? It is a little bit more painful. So the first thing I do is I just say, okay, let's set up where I'm supposed to go to, and then do a conditional branch based on the carry flag. So if the carry flag is a 1, I would end up here. If the carry flag is a 0, then I would end up here. So once I know the carry flag is a 0, then I proceed to check whether the 0 flag is a 1 or not. So now I use a JC to determine whether I should go to this label or not, which is reflecting that the carry flag is a 0, but the 0 flag is a 1. So I keep doing this until I get to something like this, because by this time, okay, because I have, if I perform this conditional branch, it means the carry flag is a 0, the 0 flag is a 0, the sign flag is a 0, but the overflow flag is a 1, otherwise I would not be doing the conditional branch. So this is one of these endpoints here. And if I track down the endpoint, okay, it is C0, Z0, S0, O1, L1. So at the very end point, I just load the constant into register A, because in this case, the L flag is the 10 in hexadecimal, the overflow flag is the 8 in hexadecimal. I put that into A, okay, this can be an expression, it's not a problem. And then we go to the end. The end is just a halt instruction. I could have put a halt instruction here as well. That would still fit the requirement of the homework assignment, the question, but I just chose to have an end label and put everything all the way to the end. So this is the more painful approach. because you end up with basically 16 of these cases, and you just have to kind of track which one you have worked with as you move along with this one. But if I see that your approach is right, okay, you will still get full credit because I'm not going to type in your program, assemble it, run it to make sure that it is working 100%. So those are the two main ways of doing things. How many people did it in a way that actually made use of the ALU as you try to check the flags? You'll still get partial credit. Okay, because that's just one little thing that you forgot. It's like, oh, okay.
Yeah.
Yep.
I left class and I'm like,
You'll still get partial credit. It's just you won't be getting full credit.
You realize
Yeah.
that, as I was handing you the paper, the second it left my fingers.
Yeah, that sinking feeling, huh? Well, you will still get partial credit, because you will still get partial credit if I look at your code and say, okay, if the ALU did not change the flags in the process, your code will still be correct, then you'll still get partial credit. In other words, someone who gives me 20 no-op instruction will still getting a 0 out of this question. I think that's fair. Okay, so any questions about number 2? So the second approach, in a way, is kind of interesting because the only instructions that I use are the conditional branch instructions, the unconditional branch instructions, the LDI instruction, and the halt instruction. That's it. I was only using a very small number of the instruction set of a RISC processor. But it is tedious.
very.
Yep, it is very tedious, but it's a very systematic approach of doing it as well. Any other questions about number 2? Okay, no questions. Let's move on to question number 3. I don't have it entered in number 3 at this point, so let me go back to exam 2, question number 3. I think this is the one that you guys have. Nope, this is the wrong class. Yep, that's the wrong class. Go to 310.
How is 440 compared to this class?
Different. Okay, we have a few people here who are also taking 440. I can let them tell you. Do you guys want to comment? Luke?
It's a lot harder. 440 is a lot more math.
It's more conceptual. Yeah.
This is more conceptual?
No, 440 is.
440 is more about math, so there are more proofs involved.
Yes.
So in the second exam, we had one proof by induction, one proof by contradiction. What else? We have probabilities. So we have certain questions about probabilities. One question on probability about flipping coins. Okay. So okay, I can tell you guys about this a little bit. So you basically, somebody is counting at a casino. Okay. So let's say at a casino they have sequences of 4 coin tosses. Okay. And somebody is secretly recording, how many of these sequences end up with 2 heads and 3 tails. Okay, and you also have a total number of these sequences, like over one evening. Okay, there are 680 sequences, of which 213 end up with 2 heads and 3 tails ordered independent. Okay, so the question is, based on just these 2 pieces of information, can you test whether the coin is fair or is it loaded? So that was the question in CISW 440. So the answer is yes, you can test it because there's a way to compute the probability of having 2 heads and 3 tails. So you just have to compare the observed frequency ratio to the expected probability. If they are fairly close, they can say, yeah, the coin is probably not loaded or it's fair. If they're off by a whole lot, they can say, oh, that doesn't look normal to me. So that's one of the questions. And then the other one is, you are transmitting 110, okay, but you can receive it incorrectly. Okay, so I give you the observed frequency of observing it. So you transmit as 110, but you might receive it as 101. Okay, so I give you the relative frequencies of how you receive that particular bit pattern, and then I ask the question of, so what is the error rate of transmitting a 1 but receiving as a 0? And also, what is the error rate of transmitting a 0 but receiving as a 1? How do you resolve that probability based on what I tell you about the probability of receiving the pattern as blah, blah, blah. So those are the questions for CISP440, which is quite different from this class.
Calculus. Calculus.
There is a prerequisite of, is it calculus or is it just pre-calculus?
I think there's a co-requisite of Calc 2.
Calc 2? We don't use any continuous math in CISP 440, but being able to understand abstract definitions and concepts is very important in that class. In a way, it is opposite to this class, because in this class we started off with transistors, right? We build ourselves up, to the kind of things that we do. But in the other class, it's all kind of really abstract. We start off with logical operators, and then set theory, the notation of how to use intersection, union, and stuff like that. So it's a bit more on the math side and than on the programming side.
Take it later in the day.
Sorry?
I was just saying, take it later in the day.
Yep. All right, so this is question number 3, which I have the solution. So question number 3 is, the dirty truth about RISC is that sometimes compromises are made due to code generation from the compiler. So even in the solution of the previous question, you can see that we have a lot of LDI, and then we have a conditional branch. LDI, a conditional branch, because we have to use a register for conditional branches. So in this particular question, it is just saying that, okay, what if I want to combine these two into one single instruction? We have one instruction that can do PC equals X. That's my unconditional branch instruction, the JNP instruction. And then we have the other one, LDI, to do X equals to star PC plus plus. Okay, so we have individual instructions to do one of these, but we don't have one single instruction to combine these into one single instruction.
I totally misunderstood the question.
Sorry?
I misunderstood the question. The way it was written, I didn't do the one instruction. I did.
What?
No, slices are different from instruction.
Oh.
A slice is a
Okay, then never mind. I did it right. I thought you wanted it all to happen in like one slice.
No, a slice is a microcode in the ROM. Okay, one slice is one microcode, 26-bit thing in the ROM of the processor.
It's like a tick.
Or you can call it a clock. Yes. Okay. So so the expected answer is like this. There are the question marks are significant. In other words, when it does not matter, you have to tell me that you can use whatever value for, in this case, PC mux, because in this case, PC mux is not important, because PC enable itself is a 0. So if PC enable is a 0, it means the program counter is not getting changed. So how you program the mux into the program counter really does not matter. Okay, so that's why the question mark is actually important in this case. So I'll be looking at your submission and compare your submission to these things here and see whether you use the question mark where, and the question mark is expected a 0. Yeah, go ahead.
What if we didn't put any question marks, but like ones or zeros for that?
You lose points.
The question says
if you don't put question mark, you lose points.
The question specifically said the use of a specific value where a question mark suffices will cost points.
Why do we have to have ALU enabled if it won't?
ALU is not.
It's 0, but can we have a question mark there?
No, because if the ALU is enabled, it will drive the output. So if the ALU drives the output, you have to look at where it goes and make sure it does not interfere with what we are doing. Well, let's check. Okay, I can be wrong here. Okay, so let's double check it. Java-jar We are looking at downloads, processor, ALU. Nope, we need to look at the overall processor. .circ. There we go. Okay, so if you enable the ALU output will be driving. So we have to click on this one and see what it can interfere with. Okay, so it looks like the ALU can operate, but the ALU also has a side effect of changing the flags register.
We don't want that.
We don't want anything beyond what is specified, right? So it still has some side effect that can, change what the previous instruction had been doing. In other words, if you enable the ALU, it will still change or override the flags register, which means, if you had a compare instruction before this one, this will override the flags register, which is not something that you should do. So that's why, for that reason, the ALU really should be disabled, because otherwise it will have side effects on the processor. Okay. I had to check because I do not remember. I'd have to look and see what things it can affect. Okay, so are there any questions about this one? Now, obviously, with this one, there will be a lot of partial credit. Okay, if you don't get the entire, thing right, you will still get partial credit. There are things that are more important than others in this one. For instance, this 7 is important. Okay, this 7 is one of the more important ones, and then some of the other ones, like you need to access RAM in the first slice. That is important as well. So certain things are more important than others, like whether the ALU is enabled or not. That is less important because it doesn't affect what the instruction is supposed to do, but it has side effect of changing something that is not supposed to change. All right. So go ahead.
Is the first slice the first instruction you had up there in the questions?
Say again.
Can you scroll up? Is it x equals star PC?
Yeah.
Is that what the first slice is?
Yeah, that's what the first slice does, and then this is what the second slice does. Now, there are a few other places that are also important, like where you put the X here and also the X here. That is important as well because that's how you parameterize the specification of the slices so that you can use one single slice to say, okay, this is the pattern of the 4 variants of that opcode. So where the X is located, that is really important as well. And then the other points would be this one here, the start location. Is going to be 50 because it is 010 for the most significant part of the opcode, and then the least significant part of the opcode is XX. Okay, we have 2 X's, right? There are no XY, so X becomes both the least significant 2 bits as well as bit 2 and bit 3, and that's why you have an X left shift by 2 plus X. This can be a bitwise OR. Okay, these can all be bitwise OR as well, because they're not overlapping. The bits are not overlapping. So whether you're adding or ORing, it will still give you the same result. Now, once you figure out the opcode itself, you have to remember to left shift it by 4 to get to the location in ROM, because each opcode in ROM has 16 slices, reserved for it. So you have to remember to shift it by 4 or multiply by 16. Pick one or the other. So if you forget any one of those things, you won't get any credit for the start location. I'm just kidding. I'm just kidding. So there'll be partial credit for identifying the constant part, the 50. I think most people will get that one. There'll be points associated with how to parameterize using X and X. Okay, so if you use only one X, you will lose some points. If you use both X's at the right places, you get full credit for that part. And also the shifting by 4 at the very end, or multiplying by 16. Those are there are points associated with that as well. So I'm going to break it down into smaller chunks, and then for each chunk you will get a particular point value for that. Is that okay? Which makes grading a whole lot more fun, because now I have 3 rows or 3 rubric pieces just for the start location. But it's easier for me too because I won't forget. This way I can grade your submissions a lot more fair because I don't have to remember. It's harder for me to grade it inconsistently across all the exam submissions. Is that okay? All right. Okay, so that's question number 3, and let's move on to question number 4. So I have to look at the actual exam for the last one. Okay, so here is question number 4. Question number 4 is saying the toy processor is not inherently safe from bus fights. Okay, so it's a statement. I did not even bother to ask you, is the processor safe from bus fights? I'm telling you right away, it is not safe. Okay, that you can potentially have a bus fight. This means there is a possibility to specify a microcode to cause more than one component to drive the same wires and damage the processor. First, specify the minimum microcode fragment that can cause this fight to happen. Include the names of the fields. Now, how do I know the fields of this particular processor? You go back to the previous question. Or you spend $5 to purchase that schematic from me, during the exam, right? I mean, I remember who paid and who did not. Okay. I'll give you my PayPal address later on.
Yeah, I couldn't find.
Just gift
where,
me. I don't want to pay that extra 3.5%. Yep, go
I
ahead.
couldn't find where the wires are crossed, on the.
Well, I'll deal with that. I'm just reading the question.
Afterwards, but during the exam, it wasn't something that we had ever brought up in class, so it wasn't something that I ever.
About bus fights.
No, we talked about bus fights, but nowhere in the preparation for this exam, they was talk about
How to fix it.
an inherent flaw in the processor itself. So that was I don't know, it made me feel unprepared for that particular question, because it's you gotta basically analyze every little bit of the process, trying to find where something's
Okay,
wrong.
we'll get to
but
that
not
part.
having a computer or anything to test each thing, it's
Yep.
The hardest part about this question was where you can't change any bit fields, so the microcode has to be the same, while the processor design isn't. Because you said it's too lazy to add any bit fields to microcode.
Right, exactly. Okay, so let me finish reading the question, and then I'll go ahead and solve the problem. So pretending that I'm looking at this question from your perspective, how I would proceed to do this. Okay, it is not 100% possible because I cannot undo what I know about the processor already. But when I came up with this question, I had to come up with the same thing. I did not design the processor specifically to have a bus fight so that I can ask a question about it later. So I designed the processor, and then later I go hey, is this really safe? I don't know. Let me find out. So I actually had to go through that process as well. Okay, so I can tell you about that process once I finish reading the question. Okay. So TAC is too lazy to add any bit fields to the microcode ROM because every time I introduce any additional bits, I have to shift things a lot with the splitter and whatnot. So I don't want to do that. And yet he worries that the student may implement the processor in hardware and cause a fire, because that's what a bus fight would do, is because you can have one component driving high, the other one driving low, and end up with a lot of current passing through that wire and potentially causing a fire. Propose a solution that can eliminate the mentioned bus fight scenario without requiring any change to the microcode implementation of opcodes, so that the content of the microcode ROM can remain as is, okay, which is the whole idea of not introducing any additional bits in the microcode. You can use tunnels, logic gates, muxes, demuxes, and etc. in your solution. Describe how to integrate your change into the toy processor. Okay, so let's go ahead and switch to the toy processor schematic and answer the first question first. Okay, where is the fight? Okay, so you look at all of these wires, okay, and you basically have to kind of guess which one can be a problem. So what you need to do is to look at the outputs. Okay, the inputs are not going to cause problems. You have to look at the outputs, because in order to end up with a bus fight, someone has to be driving a line high and the other one has to be driving the line low, which means you have two outputs connected to the same thing, and that is what potentially can cause a fight. Okay, and then the second thing as a clue is most of the time the processor does not end up with a bus fight. Because with all the instructions that we have talked about in class, we don't end up with a bus fight. Okay, so that means under the quote-unquote normal use of the processor, it is not a problem. So the output of stuff, okay, would include the output of the ALU, okay, this is an output, but this one goes only into the input of a MUX, cannot cause a problem, okay. You look at the output of the registers, okay, it goes into the input of a MUX, demux cannot cause a problem, cannot cause a problem. You look at the output of this MUX here, it goes into the input of another MUX, cannot cause a problem. So you basically track down these things, okay? This wire connects just between two components, cannot cause a problem. You are looking at something, you're looking for something that is connected to more than just two endpoints, okay? That's one of the main requirements of having a problem is it has to be connected to multiple endpoints. Or things that can both be the input and output at the same at different times. So that normally it's not a problem, but sometimes it can be a problem. So you're looking for something that can switch direction. So let's keep looking. Okay, look at this one here. This one looks like a pretty good candidate because of the sheer number of things that it connects to. So I will look into this one and see whether it's a problem. Okay. So looking at this one, you can see that it is the output of this particular demux. This is not a problem. So when you track down this wire, you go all the way around, go back to here, that is not a problem. Going into here is not a problem either because the D port of a register is an input, okay? It cannot cause problems. So you look at this thing here, this is really just a pin, it is just so that we can look at the what is on that bus. It's not a problem. So when you slide over here, okay, you can see that, it hooks up to the data port of RAM. Okay, the data port of RAM is bidirectional, which means by controlling the RAM load line, if you're reading from RAM, the data port is driving. If you're writing to RAM, the data port is read only. Okay, so that is our problem because now if you specify RAM select to be a 1, if you specify RAM load to be a 1, then your RAM will now be trying to drive the data bus. At the same time, if you program this particular demux to be first enabled and 2 having a value of 2 for the select pin, then you can potentially end up with a bus fight. So that's the combination that we're looking for. So to be more specific, okay, if I were to write this down on the whiteboard, we are looking at R register bank output 0 enable. It needs to be a 1. Register bank output 0 selection has to be a 2 because it is the third output that is causing the problem. And then we also have RAM cell, RAM selection to be a 1 so that the RAM is addressed. Yep.
You meant RO0 demux, right?
Oh, demux, DMX. Thank you. Because the selection can be anything. You can select any register as long as it is outputting, we can end up with a problem. And then RAM load has to be a 1 as well because it specifies a read operation. So these 4 are the minimum that you need in order to end up with a bus fight. Is that okay? All right, so how do we solve this problem without introducing some additional wires to get rid of this problem? Yep.
Well,
There.
I ended up giving one of them priority.
Yep, exactly. You have to prioritize and say that if I'm reading from RAM, I will make the register output, shut up. Or vice versa. There's no right solution here because, if the opcode is specifying this, it is conflicting. Okay, it's just cannot happen.
Broken opcode.
It's a broken opcode. So you just have to say, okay, I just want to avoid a bus fight. Okay, how do we make sure it does not have a bus fight? What I did not add in my question is without disabling the rest of the function of the processor. Because somebody may propose and say, just remove all the wires from the processor, then we won't have a bus fight anymore. Because now we don't have a bus anymore. So that would not be a proper solution. So yeah, go ahead.
We had to put priority, so we get like one priority over the other.
You can, well, there are a few ways to do this. Okay, so a few ways to do this. One way is to specify that when when you have this enable turned on, okay, somehow have this enable being on to be exclusive to the RAM load.
Yeah.
So you can use a gate for that purpose, right? Because you can say, okay, the input into the actual LD of the RAM can now be the output of a gate, and then the input to the gate would include your RAM load as a tunnel, but also include a register output 0 enable as the other part, and then put a negation where it applies. So that way, you cannot specify a read operation while you are also saying that you want the register bank output 0 to be enabled.
Can we use demux instead of enable?
Demux is a little bit harder to use
Yeah.
because a demux has several pins. It has 2 pins. So
I'm
you have
wondering
to.
if the test case instead of enable, can we be like if demux is set to 2 while RAM load is on?
Yes.
Just make sure nothing works.
Yep.
Wouldn't using RO0 enable disable too much because you disable output 0 and output 1 of the demux unnecessarily?
I think I have that idea.
You mean, so we basically would be disabling all 3.
Yeah, and what if we don't want to do that? That's why I think I use the demux solution instead, where if the demux is pointing to 2, whether it's enabled or not, you don't want.
We don't have any instruction at this point that will need register bank output 0 to be enabled while we are reading from RAM, so it should still be okay. Yep.
I put a control buffer on the output.
Control buffer works. Yep. That works as well. Well, a control buffer has 2 ways of operating, so it depends on whether you make it tri-state or whether you make the output a default of 0 or not.
I just attached the selection to random and negated it.
Oh, and negate it, okay. So negation may work in that case. I have to look at the actual solution. Yep. But that's but that's how you approach this problem, is to look for things that can have a fight, and then you just say, okay, I cannot allow the fight to happen, so I'll just prioritize one side and say, okay, this side can go and the other side cannot.
The hardest part was realizing I was trying to do it without prioritizing. I was trying to do it so it worked
Oh,
like every time, and it doesn't work.
it doesn't work because we don't have enough control lines to specify that.
Well, we've got issues.
I eventually got it.
You can always specify, just add more flame retardant to the hardware implementation. All right, so that's the entire exam. It was longer than I expected. I didn't intend it to be that long. Yep.
So you're gonna drop one question?
I'll drop one question. It won't help people who are getting a flat 0.
I got
It will help anyone who answer at least one question with some point values. Yep.
doesn't exactly work, right?
Okay. Any other
Pretty
questions?
sure I got like 80% of it.
No questions? Yep.
So this is actually, when is the final for this class?
Didn't know nothing.
The final for this class is in the syllabus, but I cannot remember.
Like, I was unprepared. Flip a coin.
Okay, so we're
Worse.
51.
Final for this class is Tuesday the 13th at 8 a.m.
okay. Yep. Tuesday, the 13th, 8 a.m. Yep.
Basically, I need to create a web app.
Is the final cumulative or just focusing on the last stuff?
It is cumulative, but with a focus on the last part. So the next 2 weeks or so, is going to be included in the final as well, and there'll be more focus on that stuff than the earlier stuff. Question?
Question, who would have a day for the final?
Sorry?
Review.
The one week before the final is going to be the review, so it's going to be the
Next
6th.
one.
So December 6th is going to be the review day for the final exam. Okay. Any other questions? Yep.
What's next?
What's next? All right. Well, I'm glad somebody asked a question. Okay, so this is copied directly from the schedule, okay? And so one thing that you might want to do with many of your other classes, especially if it's a transfer class, is to look this up, okay? Look up, what this means. And this is a course identification number. I'm going to look it up. Okay, by college. Okay. Descriptors. And we want to go to computer information science. There's a way that I can find it. Okay, let me find out how to get there. Descriptors, courses. There we go. We want to look up computer information science. Say filter. Okay, that doesn't seem to work.
There's no approved start date.
Yeah. Yeah, it's still complaining Ajax error, application list, and it's the site itself is broken, and that's partially what is happening here.
And this is for computer science.
No. This is for the entire state.
Oh, okay.
There is a place where you can look up, every single descriptor. Policy. Oh, where is it? So anyway, I'm not going to waste too much time to look it up here, but the last topic that we have to go over in this class is how the stack is used in a regular C program. Okay, so today is the 29th, which means we only got 1 week before the review day for the final exam. So the best way to do this is probably to use a debugger, and also so that we can actually look at things, okay? So this would be the best way to do it. In terms of what I intend to do with this class, okay, let me go back to the top portion here. We are currently in assembly language programming. We really should get to subroutines as much as possible. So these are the topics that I really should be covering, in this class, but there's not enough time to go over every single one of these, not in assembly code, okay? So what I'll be doing instead is to explain how these concepts apply in C and C++ programming. Okay, so there'll be a slight disconnect because we're not going to write code to do this in assembly, but we will write code in C and C++ so that we can at least understand what is going on, what is the stack, what is going on, and just a general understanding of all of those concepts. Is that okay? Okay. So we are switching back to C and C++ at this point, which is a prerequisite of this class. So I'm hoping that this does not come as a surprise to you. Okay. All right.
We're gonna have any other homework assignments?
That's a good question. I'm hoping that I can give you guys one more, but hopefully it's on stack, the use of the stack. Okay. I'm going to give you a sample program that you have probably seen many times already. So let's say it off. Okay, there we go. Int f int n. This is the Factorial program written in a recursive way. Okay, so how many people still remember Factorial? Okay, Factorial is relatively easy to deal with. So you say if n equals to 0. I'm not going to use a return in the middle of a conditional statement, so I'm going to use R as a result, and I will set R. I don't like the way it indents, but so in this case R equals to 1 because the factorial of 0 is 1. Okay, and then for the else case, R is going to be, what is the recursive way of defining factorial? The factorial of n is n times the factorial of n minus 1. Very good. Okay, so we'll go ahead and do it that way. N times the factorial of n minus 1. And then at the very end of this function, we return the value of r, which is the result. And that's, factorial. Are there any questions about the definition of factorial in this case? How many people have not seen recursion? Recursion? Anyone? Okay, so everybody has seen recursion. Okay, so we'll go ahead and finish the rest of this program. Okay. Come on. And we'll say int x equals to the factorial of 3, return 0. I don't even bother to print anything. Okay, there's no need to print anything for this program to work or to illustrate the point that I tried to make. Okay? All right. So there are several questions already. The first question is, how does a function know where to get back to at the end of that invocation? So that's one question. It saves the return address on the stack. But for people who are not familiar with that concept, then there'll be an additional question. What is the difference between the definition of a function as opposed to the invocation of a function? What is the difference between those two?
The definition is,
yeah, go ahead.
The definition is what actions are performed, and the invocation is where to start those actions.
Not quite. Okay, so we look at the word definition, and then we look at the word invocation, which is also known as a call. Okay, so a call and an invocation are basically the same thing. Okay, so what is the difference? I can have a program that has 600 function definitions, but no invocations whatsoever. Okay?
No call solution.
Exactly. In other words, I can have another function called g, right? Okay. That doesn't do a single thing. Okay. Okay, make it return something. Okay, 20. Fine. Okay. So I have a definition of g, but there are no invocations of g. Is that okay?
So it's on
No, it's inexecutable. It is loaded into RAM as I run this program, but I never
You
get
just never
G.
uses it.
It's never used, exactly. So in this case, we have several points of invocation of f. F is first invoked from the main program itself, and then is also invoked from itself. There are two places where f is invoked. Okay, so the one thing that you have to remember, okay, is there are things that are specific to each invocation of a function. In other words, until a function is invoked, those things do not exist. They are undefined and they do not exist. What do you think are the things that do not exist, undefined, unless a function is invoked?
Value of n.
The value of n, very good. Okay, the parameter n is on a per invocation basis. So as you do the recursion, there'll be additional invocation. And for each invocation, it has its own n. Very good. Good job. What else? Yep. Yep, for local variables, because even though we don't say that, the default is there's an auto in front of all of those local variables. Auto means it is going to be on a per invocation basis. Now to make that point really clear, I'm going to initialize r to -1, okay? I know it doesn't make any sense because the factorial of any number should not be a -1, but I put it here just so that it is easy for us to see which r we are talking about, okay? What else? What else do you think is on a per invocation basis? Yes, go ahead.
return address.
The return address, okay, where we're going back to is also on a per invocation basis. So those things, okay, let me just repeat what things are on a per invocation basis. Parameters, okay, whatever you specify here are on a per invocation basis. Local variables, unless you specify static, which is a very bad idea, okay? is if it's auto or by default, they're also on a per invocation basis. And then the return address where you go back to is also on a per invocation basis. Okay? So until a function is called, those things do not even exist. Is that okay? What is the ordering of calling a subroutine and returning from a subroutine? Let me just give you another example here. Okay, so here's G, and we'll make G return a void, and we'll just say that G doesn't do a single thing. And we have H, and H is just going to call G, and then we have IJ. Okay, so void J. Oops. And J is going to call H. There we go. Okay. So if I call J, it's going to call H. H is going to call G. G will return, right? So how do you call this ordering of calling and returning? I'll give you two choices. First in, first out, as opposed to last in, first out. It's last in, first out. Okay? LIFO. Okay? And LIFO in real life usually is not a very good idea. Like your refrigerator has a tendency to be last in, first out. Unless you have a very strange refrigerator that has two doors. One door to put things in and the other door to get things out. But since your refrigerator, especially when you're talking about a freezer, only has one door, right? So you tend to use the item that you just purchased, okay, like the jar of milk or whatnot, things that are in the back of the refrigerator tends to stay in the back of the refrigerator and become a colorful mowed farm. Or mowed garden, if you like, the concept of a garden. But that's because it's last in, first out, okay? Whatever you just purchased from Costco, okay, unless you're very disciplined and say, okay, stuff that I just buy, I have to clean out everything from the shelf, put it at the very back, and then put everything back in. Unless you do that, it's last in, first out. Okay? The way you load up a U-Haul truck is last in, first out. Okay? So let's just say that at the beginning of the move, you say, okay, I better remember to bring the map. So you took the map with you, and then you put it all the way at the granny's nuke, on the U-Haul truck, right? And then you load up the truck, and then you shut the tailgate, and barely, do that. And then you remember, oops, I forgot about the map. What do you have to do? Short of cutting that portion open to get to the map, you have to unload everything because it's last in, first out. So last in, first out in real life usually it's not very useful. But in programming, it is useful because in the case of this particular call sequence, we want to return from G to H, and then H back to J, and then J back to whoever is calling J. That is last in, first out. Okay? And that's also the way that a stack works. Okay? So by definition in data structure, a stack is simply something, a storage or collection, a bag, where the last thing that you put into the collection or the bag or the whatever unit you want to call that is the first thing that you retrieve. Is that okay? All right. So now let's go ahead and compile this program and figure out what it's going to do and how do we make sense of it. So we say gcc-o -g fact.c. Okay. If I think this is going to be okay, and gdb fact, just running the debugger. Okay, so the debugger is going to look at the program. I'm going to put a breakpoint on line 21. Run the program. Now I'm in main. Okay. In main, I can say print x. X has a value of 0. X is not initialized. It just so happens to have a value of 0. And then I single step. Okay, I single step into function f, and it says, this is actually really helpful. GDB tells you that we are not only in function f, but we also create in function f with n as 3 as a parameter. Okay, that is really useful. And we are on the first line inside the function f. We are about to change r to -1. So we single step, and then we evaluate whether n equals to 0 or not. N does not equal to 0, so we go to the else case where we do the recursion. Okay, now observe. Okay, now it says, we are at the beginning of f again, and this time n equals to 2. Is that okay? So my question to you is, how many invocations of f do I have at this point? We have 2 invocations. Very good. Okay, so we have 2 invocations of f. One invocation with n equals to 3 as a parameter, and this one with n equals to 2 as a parameter. Okay. But how do we see that? Because as far as we can see, this is the beginning of f, and I can only see this is one invocation of f. How do I know there's another invocation of f? Now we can see because we have it here, but you can kind of imagine that if your function is really long, this would have scrolled off the screen already, and it's really hard to track that, right? How many people use code blocks, or what is the other one? A GUI tool for writing the C and C++ program? Code blocks is the one. Eclipse, okay. So if you use a graphical tool, sorry? Notepad++. Okay, but it doesn't include a debugger. That one does not include a debugger. But with a GUI debugger, you cannot even scroll back and say, oh, okay, we already have one invocation. In other words, with a GUI tool, it's even worse than this, because you cannot look at the trace of your single stepping. Do you see what I mean? And you can only see that I'm currently at the beginning of f again. Okay?
So the current state of the database.
Yes, but not all the previous one. Okay, so we single step a few more times. Because n is 2, we're going to do the recursion again. Oops. No. Single step, single step, single step, single step, single step. And at some point, I'm going to go like, okay, I think I'm lost. Okay, I have lost track of the number of invocations of the function f, because we obviously have called it quite a few times already. Well, I can actually count. Okay, the first time is with n equal to 3, n equals to 2, n equals to 1. This is the last one where n equals to 0. Okay, so we should have 4 invocations of f, at this point. But your debugger is not going to show you, visually, or is it? Okay, so in GDB there is a really useful command in the debugger itself called BT, or backtrace. Okay, so BT is a command that you can type in GDB, and what it does is it will give you a backtrace of everything. In other words, we got to where we are at this point, which is line 5 in the file fact.c inside the function f. But how do we get here? It was called from Factorial on line 11 with a parameter of n equal to 1, which in return came from line 11 again, but when n equals to 2, which got to that point when from here, which in return came from main on line 21. So BT is a very, very useful tool when you're dealing with recursive subroutines, because it doesn't just show you where you are, it tells you how you got here. All the steps in between, it will show you. Is that okay so far? So let's just say that, okay, I cannot remember in invocation pound2, the value of variable r, what is it at that point? Okay, well, we kind of know because r is initialized to -1, and until we are done with the recursion, it doesn't get a new value. But let's say we don't remember, okay? And I say, okay, but I want to know what is the value of r of this particular invocation. And what do we do? You can select a frame, okay? A frame is basically an invocation, okay? So when we use the term frame inside GDB, it is the same as a invocation, which is something that is currently active. So now you can say frame, okay, frame2, okay? And you say frame2, and it will get you back into the context of frame2, even though the program is still executing at the last frame. It is giving you the context of frame2 so that you can investigate what the values are in frame2. So we have a few things that we want to examine. The first thing is, what is n? Okay, n is 2 in frame2. Does that make any sense? Well, it is pretty clear here, right? In frame2, we have parameter n being 2. So that's consistent, okay? Let's look at r. R is -1, makes sense, okay? But how do we know this r is not the same thing as the r of the other invocations? Because I can switch to another frame. For instance, I can switch to frame 1 and say, what is R? It is also -1. How do I know this -1 is not the same as the other -1? Yep.
That $3 or 4?
Yeah, what's that?
No, the dollar sign, they're really just here so that I can refer to the result of the previous thing easily. So it's not really useful for anything else. So the dollar sign is really just, I have a shortcut to the result of the previous inquiry. Okay? But how do I know I'm dealing with a different R? Because that's one of the main thing about recursion is every single invocation has its own local variable. How do I know that? What about the address of R? Would that be able to tell me which R I'm talking about? Or at least be able to tell that they're different?
It's got its own address.
Yeah.
Yeah? Okay, so
They
let's...
would be in a different memory location since they're different.
If they are the same R, they would have the same address. If they're different Rs, they would have different memory locations. So let's do that, okay? So let's go back to frame 0, which is the top frame where we are currently at, okay? And we say, okay, let's not look at R, but the address of R, okay? Some mumbo-jumbo hexadecimal number because it's a 64-bit address, okay? That's basically what it is. So now we switch to frame 1. And we say, okay, tell me the address of your R. Okay, this is the R of frame 1, which is a different invocation. Are they the same?
No.
They're not the same. Okay, which one is higher? Frame 1.
The frame 1 is farther this way.
Well, the
I mean,
number is bigger,
right.
right? This is a 19C, the other one is a 16C.
That's further.
So frame 0 has a lower address than frame 1. Okay? If I go to frame 2 and do the same thing, can you guess what that is going to be? So I switch to frame 2, print $&R. I will press the enter key once we have a guesstimate of what it should be. Okay, so we have
3.
6 and 9. What's going to be the next
22.
one? This is hexadecimal, by the way?
Yeah, so it should be 0x7 FFE22.
No 22 in hexadecimal.
Yeah.
22.
It's gonna be
it's gonna be
CC.
Okay, so what is the value between 6 and 9? What is the difference?
Oh, it's letters.
3, right? It's off by 3, right?
Three.
So what is 9 plus 3?
C.
We know it as...
CC.
Yeah, exactly. So it should be
1
CC.
CC.
Yeah, 1 CC. So let's check whether that makes sense or not. Okay? Yep, in fact, it is 1 CC. Okay, so this is confirming a few things. Okay, first of all, each invocation has its own R. Even though they have the same value, they are different variables. Okay, that's the first thing. The second thing is there seems to be some kind of a pattern here. Okay, if I go to frame 3, okay, and do the same thing, what do you think that this R is going to be?
FC.
It's off by 3.
We're gonna have to
2 0 C.
No, you're right. Okay, F is correct. Okay, F is correct.
Yeah.
Because it's plus 3, so C plus 3 is D, E, F. Okay, so
Yeah.
F is correct. Okay, let's double check. In fact, it is. Cool. Okay, so when you look at memory, okay, so I'm going to erase this part here. You can see how the space, now by the way, this is all a part of the stack. Okay, this is all in the stack of your computer, of your particular program. So what we're observing here is frame 0 has the lowest address. Frame 1 is on top of that, frame 2 is on top of that, frame 3 is on top of that, and then on top of this one is going to be frame 4, but frame 4 is where main is. This is F, 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 and this is F as well. So we have 4 invocations of F nested, but we only have one single main because that's how we get the program started.
This is the other way around.
What?
It's not the other way around.
What do you mean by the other way around?
Isn't main supposed to be the first one?
Because it has to return back to main.
You put main as the highest
Yeah,
address.
isn't 4?
No, main has the highest address. Okay, main has one local variable, doesn't it? It has X as a local variable, right? Let's check that. Okay, so we go frame 4. We need main, and we say what is the address of X. Now the pattern doesn't really continue anymore because it doesn't have the same structure, but you can see how local variable x in main has the highest address compared to the R's of f. Okay, but that's telling you something. When the stack is empty, is the address high up. As you allocate, it goes down. In other words, the stack does not grow up, it grows down.
Is the
Yep.
stack contiguous in memory?
It is contiguous in memory. So the best way to draw a stack, okay, the best way to draw a stack is to draw your container like this. And as you put items into it, you fill up the top end first. So the main is here because it's the first function being called, and then the first invocation of f is here, the second invocation is here, the third invocation here, the fourth invocation is here. So high memory address goes that way, low memory address goes the other way. Yep.
So can I tell Raj he's been drawing his stacks wrong this whole time?
No, you just have to rotate your head 180 degrees, then it looks right again. Yep.
So 0 is executed first, or resolved first?
No, frame 0 refers to the current frame. So as you do more recursion, the current frame, the last frame that you push on the stack is always referred to as frame 0, which is where you are, where the execution point is.
Okay.
So everything else will change according to, so as I return, this one becomes 1, 0. As I return from here to here, this one becomes 0. So frame 0 is where your current execution point is. I'm only using the command frame in GDB to control which frame I am examining, but not which one I'm executing. You're always executing at the very last one.
So we're returning to a higher address?
As you're returning, the address of that frame has a higher address.
That's weird.
But it works out really well now. But this is not unique to the Intel processor. It is actually the way it is done regardless of the architecture. Sorry? Oh, we are running out of time. I just realized, I just look at the clock and go like, oh, we are running out of time. So I am going to continue this over at the lab because, since we are running out of time, I'm going to use every last bit of time to cover more topics.